Good morning, John Gelkison here. I'm shooting a series of videos on coefficient of drags, graphs, and today I'm shooting on a fifth graph right over here, which is 0.33, and it's for a blog I'm going to do at EV World, and this is going to be a supporting video for it. And the reason I wanted a 0.33 coefficient of drag graph is this is where most cars live, right here at the far right. And our graphs are in increments of 0.05 CD. So as you go down here, you go from 0.33 to 0.28, and then you go down to 0.23, and then 0.18, and then 0.13. And as you can see, my whole thing here is extended so far that I've had to I have to stand out of the field of view to get them all in. So anyway, this middle one here, and it's labeled here, Tesla Model 3 stock CD 0.23, is right here. And the one to the left of it is the 0.18. This is a Tesla Model 3 with a boat tail and wheel covers, which gets the drag down to 0.179. And the goal of that project is to do 100 miles per hour to 100 miles per gallon right here. The graphs go up to 100 miles per hour. And over here is our reference graph, which is the 0.13, and that's about as low as you can go with a reasonable vehicle. You really have to pull out some stops and you have an excessively long boat tail. And but it's doable, and it's our baseline reference on about as slippery as you can get. And this here is a Tesla with a Nissan Leaf body, basically, or some similar shape, that gives you a drag coefficient of 0.28, and it is as I pointed out in the last video I shot, if you add a roof rack and a carry-all pod for hauling skis to your Tesla Model 3, you've effectively moved the drag over here to Nissan Leaf territory. There's a lot of cars that live in this area over here. I'm probably going to get this wrong. I don't have a list in front of me right now, but one comes to mind is a Chevy Bolt. Most standard production cars fall somewhere in the 0.32 territory or something like that. And as you can see, at 100 miles per hour, it would take 51 kilowatts to do 100 miles per hour. Your MPGs for an electric vehicle with a Tesla drivetrain would be 64 miles per gallon, and the range would be only 146 miles. Now a regular Tesla, for example, has only needs 38 kilowatts to do 100 miles per hour, and it has an 86 mile per gallon return with a range of 197 miles. But by adding a boat tail and lowering the coefficient of drag to 0.18, you basically end up with 100 miles per gallon at 100 miles per hour, and it only requires 32.7 kilowatts to do that speed, and your range is 230 miles. And with an ideal body form, you would end up at 122 miles per gallon, requiring slightly less than 27 kilowatts, and your range would be 280 miles at 100 miles per hour. So you can see there's a vast difference between these, 122 miles per gallon and 100 miles per hour, all the way up to 0.33, which is 63. So what you're looking at here is a range of a doubling of efficiency. To go from here, where most cars live, down to here, you would literally double the efficiency of the vehicle. And the Tesla falls right in the middle. So we got a range of this is 0.05, this is 0.1, 0.15, 0.2. So now some of the other factors you need to look at here are the internal friction, which we've labeled the same. Now this is just for ease of calculations. There would be minor differences, but they would barely show on this graph, so it's just not worth going to all the trouble. And the rolling resistance is basically linear. It's based on tires also, so different tires would have slightly different rolling resistance. But the major forces affecting your vehicle at speed are aerodynamic forces, as you can see. And they really get quite significant way over here at 0.33. And they're only about 50% at 100 miles per hour, a little more than 50% at 100 miles per hour with this lowest form here. Over here with the body that we're wanting to work with, the add-on boat tail and so forth, they're about 50% at 80 miles per hour. And with a stock Tesla Model 3, they're about 50% at 70 miles per hour. So as you go 0.05 in drag coefficient in any direction, the effects move about 10 miles per hour. The other thing I'd like to point out here is if you look at this graph over here where the orange diverges is around 20 miles per hour, and then it becomes significant at 40 miles per hour and on up. But when you're looking at a form here, let's say a regular Tesla, it still emerges at 20 miles per hour, but it doesn't become significant up until about 50 miles per hour. And way over here, it doesn't become significant until about 70 or 80 miles per hour. So the form we're after would be a compromise between these two, of course, and it would it'd only start to become significant at around 50 to 60 miles per hour. So there you have it. I've worked out the range, the miles per gallon, and so forth with each of these shapes. And so the one I'd like to go over with you is at 70 miles per hour, which is a speed that most of us would travel on the interstates and would be of significance to us. With a Tesla Model 3 at 70 miles per hour, we're looking at 133 mpgs in a range of about 305 miles per hour, or excuse me, 305 miles, which is about where the car is rated at for highway miles. I think it's about 68 miles per hour is the speed that you'd have to look at. With our modified Tesla at 70 miles per hour, we're at 142 miles per gallon and 153 miles per gallon and 350 miles of range. Okay. But if you took the body off of Tesla and replaced it with a Chevy Bolt-like body that had 0.33 drag coefficient, here's where you'd be at 70 miles per hour. And that would be 108 miles per gallon and 246 miles of range. And if you wanted to improve on it slightly, you'd go to a Nissan Leaf, which would be at 120 miles per gallon and 173 miles of range. So, for I just think there's a lot of confusion in the press that I see out there when they discuss efficiency of electric vehicles and their performance. And all these things are interrelated, the weight of the battery, the power of the motor, and so forth. But the basic thing the car sees traveling through the air is aerodynamic drag, rolling resistance, and internal friction. And that's the secret sauce to Tesla, and it could be improved upon. And the only reason a Nissan Leaf or Chevy Bolt doesn't perform as well, doesn't have the highway range, doesn't have the high top end speed, so forth, is the body shape alone. Yes, there are differences in the motors and batteries. Tesla has better motor and batteries, I'll grant that. But this is the predominant factor that has to do with performance, is aerodynamic drag. And if you can lower your coefficient of drag, you can improve your top end, and at all speeds you'll have less power consumption than you will with a higher drag form. And again, as I stated in my last video, putting a roof rack on any vehicle is the worst thing you can do. That's where the velocity of the air is the highest, is over the top of the roof. And as an example we gave with the small pod carried on top of a Tesla Model 3, it moved the drag all the way over to 0.23, from 0.23 to 0.28, and it shifted everything by about 10 miles per hour. In other words, you'd have to go 10 miles per hour slower to get the same performance. So this is what I have for you today. Now, one of the significant things here is my numbers on these last two graphs are all for if these bodies had a Tesla Model 3. So for example, a Chevy Bolt or a Nissan Leaf doesn't have a 75 kilowatt hour battery pack, so the numbers on the range, for example, would not be correct for those vehicles, because what I'm saying here is a Tesla Model 3 with these body forms on it. That would be its performance. So I'd have to do a whole new set of calculations